All right, Chemistry 3101. This is Chapter 2, which deals with molecular representations. And organic chemists need a few different ways to represent molecules. And as we go through the chapter, it will become abundantly clear as to why organic chemists like to have more than one way to represent molecules. So some of the ways that we can represent molecules are to use Lewis structures. We covered these in Chapter 1. You also would have looked at Lewis structures quite extensively in General Chemistry 1. And Lewis structures are great, but they're really only practical when we're dealing with small molecules. If you were to, say, look up the molecular structure of, many marketed drugs, let's say a prescription drug, many of them have, are just big molecules. And so it would be very difficult, or it's more time consuming to represent them with Lewis structures. Partially condensed structures can, help you get around some of that in that we don't show carbon-hydrogen bonds explicitly. Let me show you what I mean. If you look at this structure down here on the bottom, this is isopropanol or isopropyl alcohol or rubbing alcohol. And this is a Lewis structure where we have every bond drawn out explicitly, and we have the lone pairs put in there, of course. When we go to a partially condensed structure, like I said, we leave out the carbon-hydrogen bonds. So you can see that we had all the carbon-hydrogen bonds were included in here, every single one of them, but now we've bunched them together. So instead of saying, okay, I've got carbon with 3 hydrogens, and I draw them out explicitly, I put CH3 like this. Instead of writing out this carbon with all 3 hydrogens explicitly, I write it as CH3. Now notice that the one on the left is kind of like backwards from the one on the right. The reason why they chose to write it like this is because they wanted to demonstrate that the carbon here is attached to this central carbon here. So you'll see me do that throughout the class. And also this carbon here is attached to 1 hydrogen. And you see that they even chose to leave that, bond in there. They could have eliminated it. They could have drawn the structure like this, condensed this one and then drawn this like, just a CH. And so this one's kind of a partially condensed structure, isn't it? But anyhow, they've also eliminated the bond between the oxygen and the hydrogen, right? That one was left out too. Okay, so they left that one out and it's, kind of covered in here. And again, the reason that we do that is just because it's simpler, right? Everything that we can leave out saves us a little bit of time. Well, you can condense a structure even more than is shown with this partially condensed structure. If we use what's called a condensed structure, we leave out all single bonds. We just cut them all out together. Notice that we're cutting out single bonds. It doesn't say anything about leaving out double or triple bonds. I'll get into that later. We never leave those out. Groups of atoms are clustered together when possible. So you kind of get a feel for this as you see more and more condensed structures of the ways that you can condense molecular structures. But you see that the central carbon here, if you will, is attached to 2 CH3 groups. And so those are bunched together, right? We have both of the CH3 groups inside these brackets. And since there's 2 of them, we use this subscript 2 outside of the brackets to point out there are actually 2 of them. And then we have the CH, and then we have the OH, and we've eliminated all of these single bonds. They're all gone inside this condensed structure. Now, what's great about Lewis structures, partially condensed structures, and condensed structures is that they give us information about the structure, right? They tell us about the structure. In fact, if you look at their names, they all have structure in them. If you look at what's called a molecular formula, which you also would have looked at, Avogadro's number of times in general chemistry to calculate molar masses, a molecular formula doesn't tell us anything about the structure of the molecule, right? It doesn't tell us anything at all. In fact, C3H8O, it might be isopropanol, it might be isopropyl alcohol, but it could also be 1-propanol, and it also could be ethyl methyl ether. So it could be 3 different compounds. And so we want to be cautious when we use molecular formulas, right? They can be handy sometimes in organic chemistry, but if we're talking about structure, they are usually not handy. Okay, we're going to stick to either the Lewis, the partially condensed structure, or the condensed structure. So you need to be aware of all of these types of structures. Well, let's take a look at a practice problem where we have to practice drawing a Lewis structure from a condensed structure, right? You see these are fully condensed structures. This one and this one, I don't see any single bonds in there. So let's take a look here. The first thing I notice about this one is that we have 2 CH3, CH2s, right? We have a subscript 2. That means we've got 2 of these, and they're both attached to this carbon with 1 hydrogen. So let's start with that. We're going to draw the carbon that has 1 hydrogen. Maybe I'll color code it. So we have a carbon with 1 hydrogen. This might not be pretty, but let's give it a try here. Then we've got a CH2, CH3, and we've got another CH2, CH3. So let's fill in all the hydrogens here. Again, these might not be the most beautiful thing in the world, but we're going to get the point across, aren't we? There we go. So we've got those 2. Okay, after that, we have a CH2. So we're going to put that in here. We've got a carbon with 2 hydrogens attached to it. After that, we have another CH2. So we'll put that in here. And then lastly, we have an oxygen and a hydrogen. So there you have it. We took that structure and we were able to convert it into a Lewis structure. I'm trying to select that. There we go. All right, we'll move it up here. All right, give me a thumbs up if you follow me on that. Taking that condensed structure and making a Lewis structure from it. And if you have a question, of course, stop me. Usually these are, I don't like to think that anything is overly intuitive in organic chemistry. I'm not that crazy. But I think that these are, relatively intuitive. But again, if you have a question, don't hesitate to ask me. All right, let's take a look at the next one. We've got this carbon here, which I'm going to highlight in blue. Okay, and then we've got what? We've got 3 of these CH3, CH2 groups attached to it. So I don't know if I have enough space here. Let me maybe move it over. Move it on over. There we go. So we've got 3 of these. So we've got CH2, CH3, CH2, CH3, CH2, CH3. Now let's fill in all the hydrogens. And I know what you might be wondering is there a faster way to do this, Mr. Dion? Do I have to do this for the entire year? And the answer is absolutely not. There's a much faster way to draw these compounds, which is called a bond line structure, and we're going to get to that soon enough. Okay, and then next you have the oxygen and the hydrogen. So we'll put that in here. We'll put our lone pairs on our oxygen, and there you have it. So we've gone from these fully condensed structures to Lewis structures. Now, if you can do this, I mean, the world's your oyster. That means you really have a good, solid understanding of connectivity, from a fully condensed structure going to a Lewis structure. All right, there we go. Well, let's move on from there, and let me introduce what we're going to use 99, well, maybe 90% of the time in this class, because Lewis structures are really impractical if you want to represent a compound like amoxicillin, which is an antibacterial used to treat different, bacterial infections. It's one of the most commonly prescribed antibiotics in children. A pill only costs between, I don't know what the cost is, probably a nickel, between 2 cents and 10 cents, something like that. So it's really cheap. Anyhow, so let's see here. If you have amoxicillin, it looks like this, big giant Lewis structure, and it would be really painful to try to draw this molecule in this way. The condensed formula, if we tried to use that, it wouldn't tell us anything about the shape of the molecule. It'd be hard to represent the rings that we have here inside the molecule. And so there's got to be a better way, and that is to use the bond line structure. So here is what the bond line structure looks like. We get the Lewis structure on the top, and we have the bond line structure, which we sometimes call a skeletal structure. That depends on the textbook. I like to call it a bond line structure. I teach nursing organic chemistry sometimes, and they call it all kinds of manner of things in the book. But a bond line structure, what's great about the bond line structure is not only is it faster and easier to draw, it's also easier to read once you get the hang of it. And what I think is even more important, and it talks about this in our textbook, is that it helps your eye get drawn to the important parts of the molecule, which are the functional groups. Right? We have what's called an alcohol here. Here we have an amine. Here we have an amide. Here we have another amide. Here we have a carboxylic acid. And here we have a sulfide over here. So it helps your eye train in on those or hone in on those very quickly. Right? Can you see them over here? Sure. Sure, you can see them, but they're definitely not as clear. They're kind of lost in the fog there with all those different carbons and hydrogens. So if you're wondering, how do I draw a bond line structure? Well, Let me show you what you got to do here. Okay, bond line structures. Before we get into it, let me just say that bond line structures are the benchmark representations for organic compounds. Okay, they're ground zero. This is what, again, we're going to use to represent organic molecules with most of the time in this class. And so it's critical that you know how to draw bond line structures without any difficulty. You've got to be really quick at it. If you're not, you will not be able to be successful in organic chemistry. And now I'm not saying that to be mean, because I can tell you right now that you are not the first people to learn this. You won't be the last people to learn this. And all students, I find, are able to master bond line structures usually pretty quickly. You know, you get the hang of it after you give it the old college try. All right, so how do you read and draw bond line structures? Well, each corner or vertex where two lines meet and every endpoint represents a carbon atom. So over here on the far left, we have a total of 6 carbons. Why? Because like I told you, every time two lines meet and we have like a vertex or a junction or an angle, this means that there's a carbon here. And the end of every line represents a carbon. So we have carbon, 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 right? We have a total of 6 carbons. The same thing here with this molecule. Even though there's a double bond, this is the end of a line, this is the end of a line. This is an angle, right? Right here, there's an angle. And so that represents a carbon here, and that represents a carbon. Even if we have a triple bond, wherever you have the junction between a triple bond and a single like this, there's a carbon here. You have the same thing here, a triple bond going to a single, so there's a carbon here, and these are two end of lines like this. Now, when I teach nursing level organic chemistry, one of the first things I tell them is that carbon always has 4 bonds, right? Carbon has 4 bonds. And so for all of these carbons that I have highlighted in blue, all you have to do is look at the number of bonds that are attached to them. And then from that, you can figure out by process of elimination how many hydrogens are attached to them. Let's say you have carbon number 2. Well, it's got 2 bonds, right? It's got this bond and this bond. If carbon always has 4 bonds, the bonds that are left out in bond line structures are bonds to hydrogen. Therefore, there will be 2 bonds to hydrogen here. There's going to be 3 bonds to hydrogen here. Let me ask you guys a question. How many bonds to hydrogen are there on carbon number 4? And it's not a trick. How many bonds to hydrogen would there be for carbon number 4? There would be 2 bonds to hydrogen. Yes, thank you. Absolutely. Right, we have a bond here, and then we have another one here. We have one here, okay, like this, right? Like this, and this. If we look at the next molecule, right, the carbons on the end, they both have 3 more bonds that we need. But if we look at this carbon, carbon 2, it's already got what? 1, 2, 3 bonds to it. So it only needs 1 bond to hydrogen. Oops. We only need 1 bond to hydrogen, and we only need 1 bond to hydrogen here. We have 3 here. What about the alkyne, right? The one with the triple bond. This is called an alkyne. How many bonds to hydrogen are there on this carbon here, carbon number 2? How many bonds to hydrogen would there be on this carbon? Yeah, exactly. 0. None, right? Because these carbons are sp hybridized. So the only bonds to hydrogen would be the 3 on the end, like this. Now, before we can move on, I want to discuss the bond angles here with these different carbons. Okay? When you have an sp3 or an sp2 hybridized carbon, okay, you always draw them in a zigzag format. So if you look at the first 2 molecules, all the carbons are either sp3 or sp2. So we draw everything as a zigzag, right? All of these carbons in this molecule are tetrahedral. These 2 carbons here are trigonoplanar, but we draw it as a zigzag. When you have carbons that are sp hybridized, right? This is sp and this is sp. Remember that the bond angle is 180 degrees, right? These have a linear molecular geometry, and so we draw them as a straight line. Okay? There we go. You must also be able to use bond line structure language to interpret the number and location of hydrogens. And I just showed you how to do that. Right, if you look at this molecule here, this is called 2-pentanone. if you look at this carbon here, and I'm just reviewing what we've already covered, it looks like it's only got 2 bonds, doesn't it? It's got this bond and this bond, but as we just discussed, we know that it is implied that you have 1, 2 bonds to hydrogen like that. And so what you'll see is that over time, and it doesn't take long, you'll be able to almost visualize all of the hydrogens in a molecule, even though they are not represented, right? We don't see all of these hydrogens. They're not drawn in a bond line structure, but we know that they are all there. All right, let's take a look at some practice here and see if we can identify the total number of carbons and hydrogens in a molecule. We kind of already did this one. Let's take a look at this one right here. So the second one that's got a branch in it. Could anybody tell me how many total carbons are in this molecule, this bond line structure? Absolutely. Thanks, Autumn. There's 6, aren't there? Right? We have a carbon here, 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 and here, and here. So we have a total of 6 carbons, right? Each one of these carbons has to have 4 bonds. So we have 3 hydrogens here. We have 1 hydrogen here. We have 3 here. We have 3 here. We have 2 here. We have 2 here. And then we have 3 over here, like that. Could anybody tell me how many carbons are in this molecule? Absolutely. Yes, there are 6. All right, we have 1, 2, 3, 4, 5, 6. Notice that all of these compounds on the top all are C6H14. I'm not going to fill in the hydrogens on all of them, but I want you to try and do that to make sure that you understand why all of them are C6H14. All right, let's see if we can do the next one. Identify all the carbons and hydrogens in this molecule. If anybody can tally up the total number of carbons here and let me know, I'll count them myself. So somebody got 14. I got 15. Okay, I got 15. Let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I count 15 carbons total in this molecule. All right, so I say there's 15. And if you want to fill in the hydrogens, I mean, there's a lot of them. So we have 2 hydrogens here. There are no hydrogens on this carbon. We have 1 hydrogen here. We have 3 up here. We have none on this carbon. It's got 4 bonds. We have none on this carbon, none on that carbon. They both have 4 bonds. None on this one, none on this one, none on this one. They all have 4 bonds. This one has 3 hydrogens bound to it. This one has 2 hydrogens bound to it. And these ones both have 3. 1, 2, 3. 1, 2, 3. Like that. So there you go. Just a quick practice on, oops, I'm missing one, aren't I? Missing a hydrogen here. There we go. That's more like it. There you go. So we identified all of the carbons and hydrogens in this molecule that's pretty complex. You can see I could do that pretty quickly. Some other rules about drawing bond line structures. Let's take a look at them. It says if you're given a Lewis structure or a condensed structure, you've got to be able to draw the corresponding bond line structure. This is an old artifact. I don't know if the rules are on page 54. I mean, there's no page numbers in the electronic textbook, but they come where it says how to draw a bond line structure. So it's right after, it would be right after question 2.4 in our textbook. Anyhow, rule number 1, when you have sp2 and sp3 hybridized carbons, you draw them in a zigzag format, like, kind of like Charlie Brown's shirt, squiggle, squiggle, back and forth. What's another rule? When you have a double bond, you draw everything as far apart as possible. Why? Because this carbon is sp2 hybridized, and this bond angle should be close to 120 degrees. So you want it to be trigonal planar. When you have single bonds, the direction in which the bonds are drawn is irrelevant, right? Because we know that we have free rotation around this bond and this bond. So both of these represent the exact same thing, okay? Both of these molecules are identical. Rule number 4, all heteroatoms. A heteroatom means an atom that isn't carbon or hydrogen, okay? A heteroatom would mean, you know, the most common are going to be nitrogen, oxygen, sulfur, chlorine, fluorine, bromine, iodine, right? We'll put your, what else? We'll put etc. Okay, those atoms, you always draw them explicitly. Okay, so if you have an oxygen here, you can draw a bond line structure, but you draw out the heteroatom and you draw the hydrogen that's attached to it. Okay, another cardinal rule, never draw more than 4 bonds to a carbon, right? If you draw 5 bonds to a carbon, and do not draw what I'm drawing. This is very bad, okay? I feel crummy just doing this, okay? This is what we call, I learned this in the States, so don't judge me. We call this the Texas carbon, okay? When you've got too many bonds, okay? You cannot have 5 bonds to a carbon. In fact, when I was in industry and we'd interview somebody and they drew an extra bond to a carbon, we'd be like, well, thanks for coming out. You know, we really appreciate it. All right, there we go. So functional groups. Let's move on to what's called functional groups. And functional groups are crucial that crucial that you're able to identify functional groups. A functional group is a characteristic group of atoms or bonds that possess a predictable chemical behavior, right? That's going to be really important because just by looking at a functional group, you can tell how it might, I won't put will, but how it might react. And that's, you know, one of our key takeaways from organic chemistry is we wanted to be able to determine, you know, how and why molecules might react or how they do react, and we want to be able to predict. Be able to predict reactivity. So you need to memorize all of the functional groups that are in table 2.1 in the textbook, and yeah, the whole table is in there. Focus on the parts in red because there are some examples in there. You'll see that one of the columns says example and it has a whole bunch of names of different organic compounds. I'm not going to ask you how to name all the different compounds. You just have to be able to name the functional groups and identify them. Also, I posted a video or a link to a video in an announcement that I posted on Canvas that's on my YouTube channel, this video where I discuss all the functional groups if you want more information about those, because we're going to take a look at them pretty quickly right now. Yeah, I have them all in here. I think there's one that's missing, but let's take a quick peek at them. So first one, if we have a triple bond between 2 carbons, we call that an alkyne. Years ago, there was an ACS conference, an American Chemical Society conference, where the theme of the week was alkynes, and they were giving out bumper stickers that said it takes alkynes to make a world. I thought that was kind of funny. Anyhow, so an alkyne, you remember that when we discussed hydrogen bonding, we saw the bond between an oxygen and a hydrogen. We saw that in molecules like ethanol, which is found in alcoholic beverages. That is what we call an alcohol. So when you see an oxygen bound to a hydrogen, you have an alcohol. When you have an oxygen bound between 2 carbon-based groups, and I'm going to talk about what our groups are in a second, we call that an ether. So before we keep going, I neglected to tell you what is an R group, and I think it says it right down here. An R simply refers to the remainder of a compound, which is usually a group of carbon and hydrogen atoms. So it's anything that's comprised of, you know, carbon and hydrogen. Let me give you an example. Okay, you see the butanol, right? You see that this portion here is just made of carbon and hydrogen, right? That's your R group, right? If you have this ether, right, you have an R group here and you have an R group here. Again, it could be, you know, a CH2, CH3, or it could be just 2 CH3s. So that's all that it means by an R group. All right, let's move on. The sulfur analog of an alcohol is called a thiol, right? If you have OH, okay, that's an alcohol. If you have SH, it's called a thiol. Thiols are really stinky, okay? They have horrible smells. In fact, it's hard to get graduate students to do research with thiols because they literally smell that bad, okay? So a thiol. The sulfur analog of an ether is called a sulfide. So when you have a sulfur atom sandwiched in between 2 R groups, we call that a sulfide. When you have 6 carbons in a ring like this with double bonds that alternate. So it goes double bond, single bond, double bond, single bond, so on and so forth. We call that an aromatic ring, or sometimes we might call that an arene. This molecule that is shown in red here, completely in red, this is called benzene, that molecule. And the reason I'm writing the name down is because benzene comes up now and again in Organic Chemistry 1. What other functional groups do you need to know? The next one is called a carboxylic acid. Now, before I get into carboxylic acid, let me show you one thing. Whenever you have a carbon with a double bond to oxygen, we call that a carbonyl, okay? And the reason why the carbonyl is so special is because you have them in carboxylic acids, in acyl halides, in anhydrides, in esters, in amides, right? There are other functional groups that have carbonyls as well. So whenever you see the carbon or a carbon with a double bond to oxygen, we call that a carbonyl. So when you have a carbonyl and then you have an oxygen and a hydrogen bound next to that, that's called a carboxylic acid. It is not a strong acid like nitric acid or sulfuric acid. It is a weak acid, but it is an acid nonetheless. If you have a carbonyl and then you have a halogen attached directly to it, so this is where X could be chlorine or bromine or iodine. Okay, generally not acyl fluorides, we don't really look at those, but that would be considered an acyl halide. When you have 2 R groups with carbonyls attached to each other, and then you have an oxygen sandwiched in between them, that's called an anhydride, and there's a good reason why it's called an anhydride. Kind of makes you think of anhydrous, right, losing water, and we'll talk more about those later on. The next one is if you have a carbonyl and then you have an oxygen, then another R group, we call that an ester. If you have a carbonyl and then a nitrogen and R groups attached to it, and the R groups could be hydrogen, so we'll put here or a hydrogen. Here we'll put or a hydrogen. That's called an amide. Amides are really important in biochemistry because proteins or peptides are just amino acids linked together by amide bonds. The next one is an amine. If you have a nitrogen with 3 R groups, and they could be R groups or they could be hydrogens. Let me put or hydrogen or hydrogen. I'm not going to write or hydrogen on the third one because if you have this NH3, that's called ammonia, right? Everybody knows what ammonia is. All right. Other functional groups. If you have a double bond between 2 carbons, that's called an alkene. And we've seen a few alkenes. We even drew one this morning, right? I asked you to draw earlier today. I asked you to draw a constitutional isomer of cyclopropane, and everybody drew something with a double bond in it, so that's an alkene. The next one is if you have a carbonyl that's sandwiched in between 2 R groups, we call that a ketone. For example, we saw acetone. I told you the acetone when we were discussing dipole moments and dipole-dipole forces. So this molecule, acetone, is a ketone. In the last one, not the last one, but when we have a carbonyl and we have an R group on one side and a hydrogen on the other side, that's called an aldehyde. Right? I'm sure you've all heard of this one. So if you have this here, that's called formaldehyde. And I'm sure if you studied biology, you've heard of formaldehyde, which is used as a preservative. There is one more that I wrote down in my notes that's not on here. And I think it's important. And if I think it's important, it means it's fair game for a quiz or something like that. And that is a nitro. And the reason why is because nitros do come up. So when you have an R group and you have NO2 attached to it, this is called a nitro. Okay. And the Lewis structure of a nitro is really interesting because you have a charge on the nitrogen and you also have a charge on an oxygen that balances it out. Right? So you have a positive and a negative charge in the same functional group. +1 plus -1 gives you 0, and that's why NO2 has no charge. So that's a nitro group. So those are all the functional groups. It might seem daunting at first, but again, it's one of those things where if you repeat it and you practice it over and over, so we have alkyne, alcohol, ester, thiol, sulfide, aromatic, carboxylic acid, acyl halide, anhydride, ester, amide, amine, alkene, ketone, aldehyde, and nitro. And again, I have that video posted to my YouTube channel, and I provided the link for that if you want to take a look at that and get some more practice on these.